Everybody say hi, Molly.
Hi, Molly.
They're all fired up this morning, Molly. I don't know. It's like my fourth period and my third period switched around because I feel like I'm teaching juniors right now because they're always on fire. All right, 4-3. This first concept is kind of another thing that's very hard for me to explain to you, all right? So you got to be listening. Here we go. It is something called the complement, and we've learned complement before, okay? Let's say the probability of something happening. The probability of the complement we denote as like A bar, right? Okay, we do that. So we have probability of A and probability of A bar. That is the complement, yeah? Okay, whew. All right, here we go. All right, this is kind of hard for me to explain to you. What you're going to be looking for when you do this homework assignment is these words. When it says at least one, okay? At least one complicates things very, very largely. Like we don't like the words at least one. When you see that, you're going to go, right? That's what you're going to do. Exactly like that, okay? At least one makes it gross, okay? Now, it's very easy actually to do this, but it's kind of hard for me to explain to you. So I'm going to give you an example over here that's better than the example that they have, okay? And I'm going to show you kind of how this works. And we're going to talk about heads versus tails, okay? So, heads and tails. I'm going to say H or T, heads or tails. Here's what we're going to have. And we are going to flip a coin 3 times, okay? And we're going to write out the combinations that we could get when we roll or flip this coin 3 times, okay? How many outcomes are there, by the way? If I flip a coin 3 times, how many things could happen?
Four different things.
Okay, I'm flipping a coin 3 times. So 3, 1, 2, 3, okay? How many outcomes could I have gotten the first time? 2, heads or tails, right? Outcomes I could have gotten the second time?
No, I'm stupid.
2. Outcomes the third time? 2, which is not 6, That is 2 times 2 times 2 is 8. There are 8 different outcomes when I flip 3 coins, right? 3 coins, 8 outcomes. 2 times 2 times 2, yeah? Okay, so here we go. Heads or tails? I could get a heads.
Tails.
Okay, I could get a tails. I like to go in order, okay? There are exactly 4 combinations that start with heads. Okay, so heads. Okay, what else could I get that starts with heads? Heads, tails, heads. Heads, tails. Heads, tails. She's got them, all of them. Those are the 4, okay? Now it's the exact reverse for tails, right? Tails, I put at the bottom. Okay, we could get tails. What combinations start with tails? Tails, heads, tails. Okay. Tails, heads. Okay. Tails, heads. There we go. That's the one we're missing, right? Okay. Those are the 8 combinations. Yes. Okay. Now we're looking for at least one. Right? At least one. All right. There are 8 combinations here, okay? And we're looking for at least one. Should we do at least one head or at least one tail?
One tail.
At least one tail. Okay, so here's what we're trying to do. We're going to do the probability of at least one tail. There we go. I'm going to get Caleb to do this here before too long, okay? At least one tail. All right, here we go. All right, let's look at our combinations. Let's go this top one right here. This combination, is that at least one tail? No. Okay, what about this combination right here? Is this at least one tail? Is this at least one tail? Is this at least one tail? At least one tail. At least one tail. At least one tail. So every combination has at least one tail except the top one, right? Heads is the only way. So if we look at the complement of at least one tail is no tails, right? That's the only way that I will not get at least one tail is getting no tails, right? Well, what are the chances of getting no tails? 1 out of 8, right? So what's the chances of me getting at least one tail? 7 out of 8. Does that make sense? Yes? Right? Okay? Good. We can see that from the table. All right, now let's do one more. Okay? Let's do kind of a little step further without making a table. Are we doing okay? Yeah. Okay. All right, let's do one step further and let's go back over here to our PA and PA hat, okay? All right, let's say the probability of A is getting at least one tail. Out of 4 flips. Okay, at least one tail out of 4 flips. Okay, if I flip the coin 4 times, at least one tail out of 4 flips. Okay, so let's talk about that. If I'm flipping the coin 4 times, how many different ways can I write out 4 flips? 2 times 2 times 2 times 2. There are 16 different combinations. Now I'm not going to write them all out like we did with the 8, right? I'm not going to write them all out because 16 is a really long list. Okay, but at least one tail, the complement of that would be no tails, right? And there is how many combinations that have exactly no tails? One of them, and it is heads, 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 heads. That is the only way that I'm going to get, or I'm going to not get at least one tail, right? Okay, what's the probability of getting no tails if I have 16 of them? 1 out of 16. So what's the probability of getting at least one tail? 15 out of 16. Do you see that? Okay, so it's really nice to think about that in terms of the complement. That's what this section is. The complement when you're doing at least one. Yeah? When you're doing at least one. Good? Okay, now they complicate these things down below in this next example. That's why I started us off with kind of an easy one. Okay? Let's talk about this first, though. They say let A be the probability of getting at least one of something, right? Then A hat would be getting none of that thing, right? At least one tail versus no tails. Those are complements of each other, right? At least one tail versus no tails, okay? So then we find the probability of getting none, and then we subtract it, right? Like we did here, we had 1 out of 16, and we subtracted to get 15 out of 16, right? Okay? All right, so they're gonna confuse us down here below here in example 1 just a little bit. And it says a study by Square Trade found that 6% of damaged iPads were damaged by bags or backpacks. Okay? So I'm going to write that down. 6%, or I'm going to say 0.06 equals bag damage. Okay? As opposed to some other type of damage, right? Okay, these are all of them are damaged iPads, right? But 6% of them are damaged by a backpack. Like they were inside your backpack and you dropped it or something else. How else can we damage iPads? Dropping them not in a bag, right? Okay. By stepping on them, by other things, right? Okay. Like I've heard before where people have had a pencil inside their Chromebook and they slam their Chromebook and it shatters the screen, right? So that would be another type of damage. So 94% of Chromebooks or iPads, I guess, are damaged otherwise. 6% of them are damaged by being in a bag of somehow, okay? So we're talking about bag damage, not other types of damage, okay? So bag damage, 6% are damaged from a bag, all right? If 20 damaged iPads are looked at, 20 damaged iPads, we want to find the probability that at least one of them is damaged this way. Okay, so probability, at least one. At least one damaged by bag. I knew it. At least one damaged by bag. Okay, this is really confusing, so you really got to pay attention. At least one of them is damaged by a bag, yeah? Okay, what is the complement of that?
None. The one's not
Probability that none damaged by bag. No bag damage. Okay, none of them are damaged by a bag. All right? And we have 20 of them, right? Okay, the probability that none of them are damaged by a bag. This is how confusing this gets. Are you ready? Yep. Probability that none of them are damaged by a bag. Okay, so what's the chances that the first iPad is not damaged by a bag? Okay, let's back up. 94%. Okay, so bag damage is 6%. The first one not being damaged by a bag is 94% or 0.94. What is the chances that the second bag is not damaged, or excuse me, the second iPad is not damaged by a bag? 0.94 again. What's the chances that the third one is not damaged by a bag? 0.94. What's the chances that the fourth one is not damaged by a bag? 0.94. We are doing how many of these? 20. Okay, we keep going on. I don't want to type that into my calculator 20 times, right? Okay. Can we do 0.94 to the 20th power? That's not cheating. That's exactly what I want you to do, because I don't want you to type it in 20 times because you're going to lose track, right? 0.94 to the 20th power. .94 to the 20th power. What is it? 0.29. Oop, 20th. Okay.
So would that be the at least one?
Okay.
Divided by
0.29, you said? With no e to the negative power after that or whatever? It's just 0.29, okay? So it's a 29% chance that we're going to have all 20 of them not damaged by a bag. So what are the chances that at least one
So you
would
would be 71? No.
be 71% or 0.71, okay? Do you see how that works?
Yeah.
None of them damaged by a bag would be 0.94 times 0.94 times 0.94 20 times, or 0.94 to the 20th power. Confusing, kind of, right? But then you subtract, right?
That's not.
The opposite of that would be 71. I have a 71% chance that at least one out of the 20 are going to be damaged by a bag. Which makes sense, I guess, right? Confusion before we move on.
No.
Okay? Confusion, a little bit. Okay, we'll keep going here. All right. Conditional probability. All right, let's look at. I'm not going to look at this box because we've done this before. Maybe not Jackson, but we'll catch him up. Okay. We do care about Jackson sometimes. A says, and you guys, I'm sorry, you guys have to like flip back and forth because this table is not on the bottom here. Maybe we should write the table on the bottom. Should we write the table on the bottom so you don't have to flip back and forth? Let's do that real quick. Okay, so let's do plus, let's do minus. At the bottom of your sheet, do plus minus. We're going to do this contingency table. Plus minus, and then we have use and no use. We're talking about like drugs again. They do some really crazy examples here. All right, so 45, we have 25, we have 5, and we have 480. Okay? And then we're going to do some totals. So just put this at the bottom of your sheet so you don't have to keep flipping back and forth. It's a really small table. You don't have to, whatever. Okay? Let's add some stuff. So how many total people were positive? Are you still writing?
Yeah.
I'll give you a second. 70. Maddie's got it for us. Okay? I'll let you write for a second. This is just the table from the back, so we don't have to keep flipping back and forth. Sorry. Okay. All right. How many total negatives? 485. Okay. How many total users? 50. How many total non-users? 505, which makes, we've done this total before, 555 for a total, right? 555 for a total. Okay. All right. Good. So there we have that table. You don't need a new pencil. You just have two pieces now, right?
Because I don't like two pencils. I like one whole pencil. Are you gonna cry? I am gonna.
I'll give you some tape later. We'll
It's
mend
in the
it.
trash. You can have it.
We'll mend it. Oh, okay.
Thanks.
It's a perfectly working pencil. Whatever. Okay. All right. Moving on. Ready? Okay. This is conditional probability. This is like the given stuff. Okay. So check this out. If one of the 555 test subjects, we just calculated the 555 was our total number, is randomly selected, find the probability that the subject had a positive test given the subject actually uses drugs. Okay, this is the notation that they use. I don't know. This is the notation that they use. Do you see this little line right here? This line means given. That line means given. So when they use that notation, there it is. Okay, given. Okay, and before when we were doing probabilities, we would always have like our total number down here at the bottom, right? Like if I'm choosing this group of students, I would have 17 as my bottom number. But now we're not talking about the total. We're only talking about the given, right? Given a certain group of people. So that changes my bottom number. So here's the deal. The probability of a positive test result. Positive test result given the subject uses drugs, okay? We kind of work backwards and we're going to start with the given, okay? So we're not talking about all 555 anymore. 555 is not my bottom number anymore. I'm only talking about the subject using drugs. How many drug users do I have? 50. That's my total bottom number now. It's not 555 anymore. I'm only looking at the drug users. It's everything after the given the drug users, okay? Positive test result. Of those 50, how many were drug users? How many tested positive? 45. So that is my conditional probability, and I reduce it to 9 over 10 or 0.9 or 90%. One of those things, however it has you write your answer. Yeah? Okay, do you want to attempt the second one on your own?
No.
Yeah, attempt it. I'll give you like 30 seconds. This is what you're looking for. The probability. The subject uses drugs given that they had a positive test result. Okay, so try that one on your own. Don't say it out loud. Just try it, and then we'll do it here in 30 seconds. Go. Okay, we're not looking at everybody. We're not looking all 555 people. We're only looking at the positive test result people. How many were the positive test result people? 70. That is my new bottom number. It's not 555 anymore. It's out of 70, okay? Now, out of those 70, how many use drugs? 45 is the users. So 45 out of 70, and if you reduce them by 5s, that would be like 9 out of 14. 9/14 or 64%. 0.64. 0.64 or 64%. One of those answers is correct. All of them are correct, but on your homework it's going to say only one of them is correct, depending on what they want. Okay? Good? Happy with that? We've done the givens before, except Jackson maybe hasn't, because I didn't have him last year. I cannot take responsibility for you. I'm sorry. Okay? Good? Everybody else, does that look familiar? Okay, great. All right, moving on. Okay, maybe we'll do one more and then we'll stop. We'll stop before Bayes' theorem. Okay? How about that? We'll just talk about this confusion of the inverse. Okay, here we go. This example has two different events going on. It has, and this is talking about it in words, it has the probability that it is dark outdoors and the probability that it is midnight, okay? So what they're saying to you in this section is the confusion of the inverse, okay? Here's the deal. One way, it's saying if dark, then midnight. Okay, if it is dark, then it is midnight, okay? The other one is saying if it is midnight, then it is dark. Okay, I'm paraphrasing, so just bear with me, okay? If it is dark, then it is midnight. If it is midnight, then it is dark. Those two are not the same thing, okay? So we're going to look at the probability of each one of these. We're going to do P of that, right? And P of that, okay? One of those has a 100% chance of happening if, hold on, if we conveniently ignore the Alaskan winter and such anomalies. We're not taking into consideration that in some places like Alaska, it is still light out at midnight. We're saying that it is dark at midnight. We're ignoring that fact, okay? I prefaced like this whole chapter with like we're ignoring crazy weird things that happen, right? Okay, so ignore that. All right, one of those has a 100% chance of being true. Which one is 100% chance true? The bottom one. If it is midnight, it is 100% chance of being dark, ignoring the Alaskan winters and that weird anomaly, right? Okay, but is it true that if it is dark, it is necessarily midnight? No, right? So this is not the same thing. This is actually pretty close to one. I'm going to say pretty close to 0%. There's pretty close to a 0% chance that it's going to be exactly midnight on the nose if I'm talking about any hour that is dark. Give me an hour that is dark that's not midnight.
11 o'clock.
What?
2 o'clock.
11:52. 4:33 in the morning, right? Usually it's dark still by then, even in the summertime. I don't know. Anyway, okay. What else? The chances of it being midnight exactly, given the fact that it's dark, I could choose a bunch of other different hours and seconds and minutes where it is not midnight exactly. So that is pretty close to 0. Okay, now, one more thing. When you have a value that's pretty close to 0, we'll get to this eventually, but values pretty close to 0% chance, they label as 0 plus. Okay, now what that is saying is that it is not impossible to happen. It's not a 0% chance of happening, but it's pretty darn close, right? Okay, so if I were to ask you, okay, you don't know what day my birthday, well, maybe you do, but you don't know what day my birthday is on, pretend. You don't know what day my birthday is on, and you don't know what hour my birthday was on, hour and minute and second, right? Okay, so if I ask you what day and hour and minute and second was I born on, you probably could guess it, right? But it'd be pretty close to a 0% chance of that happening. It's not impossible. You could do it, but it's going to be like a 0 plus chance of that happening, right? So they write it as 0 plus because it's like going to be like 0.000000001 maybe, right? It's not 0 because it could happen, but it's 0 plus. Like they write that as 0 plus, okay? Because it's such a small number that we don't care anyway, right? But it's not 0 exactly. Okay, so there's that. All right, we will stop and we'll start Bayes' theorem tomorrow. I will record this section and ship it off to you in Google Classroom. The homework is online. If you want to go ahead and begin that, you can do like a large majority of it or get caught up on 4142 if you are not already. Okay, do that. Everybody say bye, Molly.
Bye.